Welcome to the 6th episode of the OpenCL video series. My name is Dave Gohara, and I'm with MacResearch.org, as well as with the Center for Computational Biology at the Washington University School of Medicine in St. Louis. In this episode, we're going to talk about shared memory kernel optimizations, and really what that means is we're going to be sort of bringing home all of the concepts that we've talked about thus far in terms of shared memory, what it's used for, how to take advantage of memory layout, things like that. And so if you've understood what we've talked about in that regard so far, then this should be a very simple extension of that and kind of give you an example of how it's actually used in practice. If you're still having some troubles with the concepts, hopefully this will help solidify them in your mind by actually looking at an example and seeing how it makes a difference, and that in fact it can, using shared memory can in fact make a big difference in the efficiency with which calculations can run. I'd like to, then I also want to point out, of course, that if there are any questions or comments, feel free to either post them to the MacResearch.org forums or by emailing me. My email address is up here on screen, and letting me know. I'll either answer the question directly or I'll try and address it in a future podcast if it's something that a lot of people are asking about. And so with that, I'd like to just do some quick housekeeping. Once again, I'd really like to thank Macias, our hosting provider, for really giving us some great service and for really doing a fantastic job for us. If you're looking for application hosting managed services, they're a great group of guys to deal with. The service has been phenomenal. They've really been a pleasure to work with, and we appreciate them working with us, and we appreciate their support that they've given to MacResearch.org. So thanks again, guys. Since we had the last podcast was all Q&A, there's really no Q&A this time. So let's just get to it. In this podcast, we're going to do, you're going to be able to download an Xcode project that's derived from some real-world code. The code example comes from a program called APBS, which I work on in my day job, and it's used primarily to understand the electrostatic properties of biologically relevant molecules. And the reason why this is important is for a number of things, but for understanding, say, protein-ligand interactions, drug design, understanding how therapeutic compounds might interact with a molecule of interest, in molecular dynamics as well, things like that. And so the code snippet that you're going to see here is derived from that code, and so you'll see a real application and how we've used OpenCL to really increase the performance of one of our computations. This is a really good example because the example actually uses shared memory to get a lot of performance. In fact, it's a really good example first because it shows you that you can, in many cases, you can just take your code, your C code if you have it, and just move it over to the GPU and out of the box get some really great performance. But then it shows you how to take advantage of certain features of the hardware that really allow the code to shine and get a lot of performance, performance that you otherwise wouldn't necessarily have access to. And so with regards to shared memory, we're going to use this to take advantage of accessing the same read-only kind of data over and over again, and shared memory allows us to speed up that process quite a bit. But then this example is also good because it also highlights the use of synchronization points and how you communicate between work items in a work group, and how you coordinate all of their work and effort to do some really sort of amazing things. And so this is I think a great example for all of these, for bringing home all of these kinds of concepts. Now, the calculation that we do is that we're going to talk about here is we do perform in the program a complex set of calculations that are broken up into stages. We're really only going to look at one stage here, and this is the boundary value setup of the problem. And so the problem that we're generally looking at, in our case, we're looking at biological molecules, so we're really talking about atoms, and we have to discretize our problem to a grid. And how we deal with the grid points that are internal to the grid are different than how we deal with the grid points on the edge of the grid, and or not just the edge, in the faces, the boundary of the grid. And the way we treat the calculation on the boundary of the grid is completely different than how we do it internally. And so it's very important for us to make sure that we're doing the calculation properly, but it's also very computationally expensive how we treat the values on the boundary. And so we need to make sure that we're doing this as efficiently as possible. Now, the calculation in this case, the way we do it is that for every grid point, we're going to be calculating a value over all atoms in our model. Now, I put atoms in quote in this because I don't want people to think that, oh, what we're talking about here is only relevant to this one particular case. What we're talking about conceptually is applicable to all kinds of problems. And so even if you don't deal with biological molecules, but you deal with particle type problems, or problems that that are conceptually thought of as particles or even grids and things like that, then these kinds of concepts will be directly applicable. And then of course in this calculation we're also going to show performance between the CPU and the GPU. So what are we talking about initially? Here we have a typical molecule of small to medium size. In this case, this is from PDB 2AKG, and it's the G quadruplex from oxytrichonova. So it's a solution structure that was determined of this molecule, and the details of the molecule itself aren't important. What's important is that we have a bunch of atoms in this case, and in setting up our boundary value problem, we put these atoms into a grid, and here I'm just showing the boundaries of the grid, but we have a grid point here, a grid point here, a grid point here, and we're going to need to calculate the contribution of all of these atoms to each and every grid point. And there are a couple ways to do this kind of calculation. On a serial machine, you can either, actually I'm getting ahead of myself, we can either do this from a grid-centric approach or from an atom-centric approach. Now, in the atom-centric approach, what we're saying is that this atom is going to calculate the value for this grid point. This atom is going to calculate the value for this grid point, and then we're going to iterate over every atom and calculate the contributions to every grid point. So this guy would be calculating, this grid point, then if there was another grid point, it would go on to that one, and then, we do this. Now, in a serial calculation, the atom-centric approach works just fine. There's no problems here because each atom is going to be accessing a grid point, serially, one after the other after the other. In a parallel system, this is a not so efficient approach, because you can imagine that there will be times when this atom might be accessing this grid point, but this atom may also be accessing this grid point, and this guy might happen to be accessing it. And so if they're accessing it, modifying the value, remember this is a rolling sum, we're calculating a summation on this grid point of the contribution of every atom to it, that we end up with this guy might be overwriting the value that this guy just put there. And so what this requires in a parallel environment is that we have to use either locks or reductions. Now, on a CPU, reductions can be relatively fast. There's a little bit of overhead to it, but doing a sum across an array, we can cache each of these values into their own array and whatnot, but that will come at a cost of increased memory. In the case of a lock on a CPU, locks are extremely expensive in a multi-threaded environment. They're not well, they're expensive, certainly compared to the size of the calculation that we're doing, and so we want to avoid them. On a GPU, we don't have access to locks, and reductions are very inefficient to perform anyway. They're possible, and I shouldn't say they're very inefficient, but it's another kernel call, and you can't easily do summations in current GPU hardware across a bunch of elements in data that's being stored in and out of the card. So this isn't necessarily the best approach. The better approach is to do this from the grid-centric point of view, because every grid point is going to is going to only be reading data, and the data we read is the XYZ position of the atom plus its charge and the size of the atom. Okay, that's all read-only data. None of that data is getting modified during the course of the calculation. The grid point value is getting modified, but it just has to know, it just needs to have a snapshot or a copy of what the values are for all of these. Now, each grid point, you might say, well, that's also a bit, bit of a problem, but since it's read-only, what we're going to do is we're going to show you how on the GPU grid points can work cooperatively to bring a bunch of data in, so increased performance of doing that, and then they can then access that data very, very quickly, do the calculation that they need, and then they can work cooperatively again to bring additional data in and do this iteratively. And this, so this is the approach that we're going to take, the grid-centric approach to this. And again, the beauty of this is that it doesn't require any locks and it doesn't require any reductions. All the grid points, when the calculation is complete, will have been fully updated, and we don't have to worry about one grid point stepping on the value, the answer for another grid point, because the value is each one of the grid points, the value for them can be calculated independent of the other one. And the reason for this will become apparent as you look at the code. And so what is the actual code? So we've taken our problem, it's a three-dimensional problem, but it's been linearized for simplicity. And so basically it's very simple. It's a double loop. For every grid point, we're then going to loop over every atom in our model, and we're going to calculate an expanded version of Coulomb's law. So it's just basically from each grid point, we're going to calculate a distance value, and we're going to offset, we're going to do a summation of every atom to that grid point. That's it. This is a very, very simple calculation. And so how do we take something like this from the CPU and move it over to the GPU? Well, conceptually, this is very straightforward. The core portion of our code is effectively the same, and our grid iteration effectively becomes our ND range, and our ND range is equal to the number of grid points. So if we had 256 grid points, our ND range would be 256. It's that simple. And so basically this is what the code in our kernel effectively becomes. And so let's look at the kernel code. In this case, our unoptimized kernel code would be something like this. We've got a grid value based on our global ID. We pull in the grid coordinates, because remember we're calculating a distance, and we pull in the grid coordinates based on our grid ID. Now we could calculate some of this stuff on the fly. We have plenty of floating point machinery. We could do that this way. This is just done for simplicity again, and some historical reasons. And once we know that, we are just doing our main loop over all of the atoms, and then we store the value out once we've done that. So each work item, okay, invokes this kernel. Okay. Now, hopefully, what you can see is that there's an inefficiency here, and the inefficiency comes with the fact that every kernel that would be executed, let's say we have a grid size of 16, so a half warp size, all right? Every thread is going to be, every work item, excuse me, is going to be executing at atom 0 at the exact same time, okay? So that means that every thread is going to have to read in a value for, serially is going to read in, this value for AX, AY, AZ. Now, they probably won't all read them in. The hardware would probably detect that they're reading in the same value. It'll do the load once, and then they'll share it sort of among themselves. But you're then going to be serializing on all of these loads for X, Y, Z, charge, and size. You're going to serialize these when you jump from atom to atom to atom. So as I go from atom 0 to atom 1 to atom 2, those are all going to be loads from global memory, and each thread is going to have to wait to service that load, okay, or wait till that load is serviced before they can continue with the calculation. And so you either have to kick off a whole lot of threads and flood the pipeline so that you overcome these latency issues, which you can do, and this might be something you might want to play with in the code, or you have to find some sort of way to bring in this data in larger swaths and do it cooperatively, a group of threads, so that they can all access this data as quickly as possible. And so this is where the concept of shared memory comes into play. Okay, so shared memory. Basically what I've done for this calculation is I've allocated a chunk of shared memory. Okay, now remember that shared memory, currently on current hardware, you only have 16 kilobytes of shared memory per SM. That means that all scalar processors, there's 8 of them, 8 cores on an SM, have to use that same block of shared memory. So you don't inherently get access to the full 16 KB. Okay, but then on top of that, you want to remember that we don't deal with typically individual bytes of data. We're dealing often with floats or ints or things like that. And so really what we get is some actual useful, the number of elements that we can actually, service might be less than that. And so you have to keep this in mind when you're partitioning your problem and you're coming up with partition sizes, how you go about setting this up. But in this case, what I've done is I've taken a shared memory block and I've allocated a block that's 5 times my local size. And in the case of this example, my local size is 64 elements. Okay, so I have 5 times 64 times the size of float, because I'm dealing with floating point data, okay, which is equal to 1280 bytes. Okay, so I have a block of 1280 bytes that's going to be used per work group. Okay, and each work group is again 64 elements wide. Okay, and this will make a little bit more sense in a couple slides, the sort of breakdown. But what I'm saying is that, and then what I do with that is I partition that into 5 groupings, because remember I have my X data, which is all linear in memory, my Y data, which is all linear, a stride of 1 in memory, Z data, my charge data, and my size data. I could have allocated 5 smaller shared memory blocks. That's fine. This was just sort of easier. It just kind of makes the code a little bit more concise in terms of having to do all the setup and overhead, what I have to allocate and things like that, and variables and whatnot. So this makes it a little bit simpler. And then what I do is I use offsets to index into this data. So we calculate a local ID. Now, again, my work group is 64 elements. That means that that means I have 64 work items in my work group. Okay, and each one of those is going to have a local ID between 0 and 63 inclusive. Okay, and when I want to calculate the value, a value that it's going to need to read, okay, to load the data from global memory, okay, it's going to be calculated based on some kind of local ID offset. Okay, now that's the initial positioning. The local ID we're going to use to index into global data, and also to index into here at some point when we're copying the data in. And then I'm going to have this other notion of offsets where I add a value to my local ID. So when I want to get to my X data, if I want to get to the first value of my X data, I add 0 to it. If I want to get to the first value of my Y data, I take my local, I could take my local ID or an ID value or something like that and add L size to it, which is my local size, which is 64. If I want to get to my Z data, I add in 2 times the L size, 3 times the L size, 4 times the L size. So I'm just calculating a bunch of offsets. This is all very straightforward stuff. If you're familiar with taking a 2D array or something and then addressing it, linearly, this is the exact same concept. That's what we're doing here. So basically, this is how I've done it. Again, there are multiple ways to do this. You could do this. You could do it with an index. You can offset it just by doing some pointer arithmetic once in your kernel. 6 or 1/2 dozen. It doesn't matter what you do. The compiler will probably end up producing the exact same thing anyway. So anyway, this is how the problem was sort of set up. And so when we look at the optimized code, just the inner loop, what we do looks a little bit more complicated. It is a little bit more complicated, but it's not It's not terribly difficult to sort of understand. So the first thing is that our loop has changed, our loop structure has changed slightly. Instead of doing iterating over every atom, we iterate over atoms plus equal to L size. Again, this is equal to 64. So we're going to be iterating in groupings of 64. Okay? And the reason why this works is, first we say if the atom plus, we just have this security measure in here, if the atom plus our local size is greater than the total number of atoms that we have, because there's no guarantee that the number of atoms we're going to have is going to be a multiple of our local size, then we just adjust the local size. Now I want to point out that there's actually, in this code, there's a bug of sorts, there's a performance bug of sorts, and I'm going to leave it to the viewers to see if you guys can kind of figure out what it is and where it's going to crop up, but see if you can figure out. Maybe I'll give the answer next time if I remember to. But there is something in here, but see if you can figure it out. And so anyway, so we just do this catch-all just to make sure that everything's okay. And then in the second sort of grouping here, what we do is we just make sure that the atom that we're dealing with, we want to make sure that it's less than, the number, when we add in our local ID value, that we're less than the number of atoms. By and large, this will be true. And so this is our copy operation. And so basically what we're saying is I am, let's say, work item 0 in a work group. Okay, I'm going to load the iAtom value 0 plus my offset. My offset is 0, so I'm going to load in the x value 0, and I'm going to store it into the shared position. I'm going to do the same thing for the y, z, charge, and size. This is all going to effectively get stored into the equivalent of the 0 position at each one of these places in shared memory. Okay, and because our shared memory, the way we're breaking it up, is a multiple of is a power of 2 or a multiple of a power of 2, we don't have to worry about any misalignment or anything like that. Everything will always be aligned in this case. So now what happens if I'm work item 2? Okay, I'm still going to load in iAtom 0 but plus an offset of now 2, and that's going to get stored into shared memory location 2, shared memory location 2 plus my L size, so 66, 2 times L size, so 130, etc. and so forth. And so what you can see, and you say, well, how is this any more efficient? Remember, the hardware is going to detect that all of these threads are simultaneously accessing data from global memory, but they're accessing sequential addresses. And so the hardware is going to say, what do I do in this case? Let me do a full coalesced load into memory. And then we're going to and then this is where we hit our first barrier. So it's going to do these coalesced loads, and it's going to hit a barrier. Now you might say, well, why is there a barrier here? Why do I need to have a barrier? So let's talk about that. So I put together a slide. Now remember, we have 64 work items in our work group, and in this case it's equal to 64 elements of floating point values. Okay, if our shared memory block was just 64, was of local size, so we had 64, so just for simplicity. Okay, remember, a warp is equal to 32 elements. So if we wanted to service the loads, all of the loads for shared memory, okay, equal to this size of 64, we'd have to break this into 2 warps. Okay, 2 warps are going to have to do this calculation because our work group size is equal to 64. All right. Now, what's going to happen, though, is that there's no guarantee that this warp isn't going to continue doing its calculation before this warp has finished doing its load. Remember, this warp is going to execute something on the scalar processor. This one is going to wait, or is going to be delayed. No 2 warps are going to execute at the same instruction at the same time, per se. So they're going to be temporarily displaced by at least one instruction, okay? But remember, we also don't service full warps. We service them as half warp, so it gets a little bit more complicated. The first half warp is going to do its load from shared memory. The second half warp is then going to do its load from shared memory, okay, to service this warp, and it'll cascade up. So basically what's going to happen is you're going to have 4 half warps that need to execute just to get 64 elements, just to get our 64 elements loaded for a single instruction. So let's say we're dealing with this line right here. Okay, we're just doing this line here in all of this. This is what has to happen just for that single load. Okay, and so what would happen if this half warp started continuing on with its calculation, or was scheduled to continue on with its calculation before this half warp had finished even loading the shared memory that's going to be needed? Well, the values are going to be wrong. The answers you're going to get will be wrong. And you can do this test. You can, try and comment out the barriers and see if you, always get the right answer. Chances are you probably won't. And so basically what this does is our barrier becomes an implicit block here that says every work item in this work group, all 64 of them, has to get to this step before any work item in this work group can continue to the next stage. This is how we guarantee that all of the data we need has been loaded into shared memory. Once we know all of the data has been loaded into shared memory, then everything within the work group is free to continue. So hopefully that makes sense. So once that happens, then we get to the point where we actually do our calculation and we just iterate over our local size. Again, this is 64. This is the exact same code, except now instead of reading the data from global memory, we're reading it from shared memory. Okay, so we're reading in our read-only atom data from shared memory, and we do this calculation. Now, you might be saying, well, wait a minute. If all of these are going to be occurring in lockstep, that is true. So every thread or every work item in a half warp or in a work group is going to every work item in a half warp is going to execute each one of these instructions in lockstep. Now you might be saying, if they're all accessing this, is this not a example? Would this not result in a bank conflict? They're all reading value 0. And remember, there's one exception to bank conflicts, and that's in the case of a broadcast. Remember, if all threads or all work items in a work group are accessing the exact same element from the same location in shared memory, that is a broadcast, and that does not count as a bank conflict. So we avoid the bank conflicts in all of this. We're just indexing in, we calculate our values, we do this over a loop, and then we wait. So now why do we have a barrier here? Well, again, remember that not all of the half warps that are going to be executing simultaneously. Okay, the hardware is going to execute a bunch of them, and it's going to say, let me just do a context switch over to the other one for one reason or another. Something might get stalled, it might be waiting on something else. I mean, who knows why it might do it, but it's going to have to context switch at some point. And so you can imagine that if the first half warp finishes, or the first warp finishes, and the second warp is still working on doing its calculation, and it were to iterate back over into the loop, you could imagine that you'd get into this situation where the data in shared memory might start getting overwritten while the previous warp might be writing to it. So as another exercise, try commenting out this barrier, or try commenting them both out and see kind of what happens, just to get a feel for how barriers work and why they're necessary. Sometimes it'll make a difference, sometimes it won't. But what you don't want to have is that kind of variability, so it's important that you understand this concept. So really, this is the code. There's a little bit on top that's not shown here, but this is the core portion of the code. And so what we're going to do is we're going to switch over to Xcode, and we'll just do a walk through the project. We'll run the example, and I'll point out a few things, and that'll be it. And then hopefully you'll have something to work with, and that'll make things a lot better. So why don't we switch over to Xcode, and we'll do that part of the demo. Okay, so Here we are, we have our Xcode project, and I just want to point out a couple quick things. In the executable portion, last time we had source code, some people had problems running it, and it seems like this was checked, and so what you want is this radio button set to project directory. If you do that, it'll find the kernel, and it will run properly from there. The other thing that I want to point out is under the build settings for this. It's currently set to 64-bit Intel, so if you have a 32-bit Intel CPU, then you'll want to obviously change that. It might auto-detect it. I'm not certain what would happen. I'm using LLVM GCC 4.2. Clang 1.0 doesn't support OpenMP, it seems, so that's why I'm using this, and you'll see where I'm using OpenMP in a second. And then, but you could also use GCC 4.2, or if you don't really care about the OpenMP at all, then you can just use Clang 1.0. And then I have OpenMP obviously turned on for OpenMP support, but that's basically it. And then just regular optimizations, I think were enabled to something like -03 or something, but it doesn't really matter. For this, well, I guess it does. You still want, some optimizations turned on, so that way we're getting a good measure of the scalar performance of the CPU code. So with that said, let's just look at the actual, and then over here, of course, we have OpenCL, the OpenCL framework included. We have our C file, and then we have two kernel files. I split this out into two kernel files. I had a valid reason for doing that initially, but it turns out it wasn't really all that valid, but I was too lazy to put them back together. So anyway, this is what I've done. So they're split out. We have our original version and then the optimized version of the kernel file. And let's look at main real quick. So we have our atoms and our grid points. Now, you'll note that I actually pad the number of grid points out to 512. Why 512? Well, it turns out that our maximum workgroup size in OpenCL is 512 work items. And so having it be a multiple of 512 is always safe in case you dynamically assign a workgroup size, and you'll see how to do that actually in a second. But so you're always guaranteed to at least be padded. Whatever you need to be padded would be padded out to 512. In general, it just needs to be it's ideal for it to be a power of 2 or a power of or a multiple. Yeah, a power of 2. Your total value, but you you want it to be a multiple of a power of 2, and or at the very least you want it to be a multiple of a warp size, which in this case is 34, and if you're on ATI hardware, the size of a wavefront, which is 64 elements. So I did 512, no harm, no foul. I think that should be fine. We allocate some memory, we generate some data. I was going to include some actual atomic data, but it kind of balloons up the download, and so it's not really worth it. And the actual values that we get out of here are terribly important, to be honest with you. So we just generate some data, and there's a function that just fills up these arrays with random numbers, and then we do our calculation. And so we start off with a scalar calculation on the CPU. It's serial, and then we do we do some timing with mock absolute time, and print out the value, print out the time for that loop. We do another version of the scalar calculation, but at this time it's actually in parallel. We do using OpenMP, print out the values, and then we do our two GPU calculations, an unoptimized version and an optimized version, and then some cleanup. So let's go up to the top of the file here. Again, just the general utility routines here. There's one that I've included that's not actually turned on in the example. I'll show you where you can turn it on or how to turn it on, and this is called device stats, and this will actually print out a bunch of useful information about your devices. So, if you're running on the CPU or if you're running on the GPU, you can kind of call this function for a specific device, and it will query the hardware and tell you exactly what it's capable of, clock frequency, the device name, extensions that it may support, etc. and so forth. So you might find that useful. So I've included it here as well. In our kernel, this is similar to what we've done before. We go, and then if you want the device stats, you can just comment out this line right there, and then when the program runs, it'll execute that. and print out some information to the screen. We load our program, we create a context, a command queue, we do a program. If there's a problem with the program, it'll print out a build log. It'll print out a build log anyway, but the log may be empty. But if something goes wrong during the building, it'll print out and tell you. This is how you can also query to see like if something goes wrong with your kernel file, because remember the kernel is compiled at runtime, so you don't get any of the warnings that you would get, like say Xcode gives you if there's a mistake in your actual code. And so it's important initially when you're debugging kernels that you might want to print out the build log, and this is how you can kind of query it and print out the information. We create a kernel for the program called MDH, and we allocate memory for what we need, including our shared memory, or the memory that we're going to write data out to as well, and all of this is, and then we do a CL finish. Now again, you don't need the CL finish, but we're actually timing these portions of the phases, and so we have a CL finish and then mock absolute time calls to get that information. And then we come in and we set up the actual kernel. Now here's the important thing, is that we have a global work size, which is equal to the number of adjusted grid points. Remember, padded out to a multiple of 512. Our local work size is 64. And remember that the global work size has to be evenly divisible by the local work size. And then we have our shared size. Now remember, if you go back and look at the, if you look at the slides, that it's 5 times the local work size times the size of float. And so this is where we kind of specify what that is, but we don't actually allocate any dedicated memory. So you'll note up here that we actually allocate memory on the device and push it out there and do those kinds of things. This actually gets allocated dynamically by the JIT compiler and then on the device specifically. So you don't have to, all you have to tell it is how much you want. You don't actually have to create it and pass in a handle like you have to do with these other memory objects. Now the question invariably comes up, what do I make my local workgroup size or my workgroup size? And a lot of this again is trial and error. Now there's a way to find out based on your kernel and the device. OpenCL can give you a recommendation back on what it thinks is a good workgroup size. And the recommended size that it'll print out, in this case on my system it prints out, for my GTX 285 it prints out a workgroup size for these kernels of 512. Now what I've found is that if I actually use 512, I can't really use it because there's not enough shared memory, but then also again in the shared memory calculation, but then there's also the issue of it doesn't help the performance at all. And so playing around with this, I found 64 to work the best, so that's kind of what I've stuck with in these examples. But you can use this to maybe dynamically get some idea of what a good work group size is. You would just move this up a little bit higher, and then you could use this to set your local work size, for example, at runtime. So that would be one way to do it. Then we go and we enqueue the kernel, and we have our kernel with an ND range of 1, passing our global work size, our local work size. It max actually turns out to be 1, so we're only doing 1 iteration of this. It takes long enough that we can get pretty reliable timings from it. And we force a CL finish on the command queue, and then get some additional timings, and then we also read back the data. And then finally what we do is we print out information about how long it took to allocate in queue, and then read the information, and then we print the total values. Now we could run this on the CPU in OpenCL and the GPU. You can do that as an experiment if you want. For the CPU code, I'm actually running the original CPU scalar code, and then I'm using OpenMP just so you can kind of see an example of OpenMP and compare and contrast how I would parallelize this kind of thing using OpenMP, which actually just turns out to be this one line of code in OpenMP, or how we do it in OpenCL. Now you might be saying, well, look at all this work I have to do for OpenCL, and look what I have to do for OpenMP. What you're going to find when we run this is that although on 16 CPUs the performance is actually quite good compared to compared to the unoptimized GPU code, it still doesn't compare to the optimized GPU code. And so, it definitely becomes worthwhile to pursue these things on GPUs until we get, 32, 64, 128 core type systems. But even then, GPUs may be even, further along. So right now we have 16 cores that we're working with on this system, and this is what we do. And so anyway, so this is basically the project, and we can go ahead and run this. And if we run the calculation, what's going to happen is, so it generates its data, and then it's going to go and then do the calculation first on the first the scalar calculation on the CPU, and this takes 20 some odd seconds to run. So it's going, it's doing its thing, it's running on a single CPU right now, and then it'll do 16 CPUs, and then it'll do the unoptimized GPU and then the optimized GPU, and those happen really, really fast. So we'll wait and see. So 32 seconds. And you can see that from the output here. So it took 32 seconds on the CPU, and actually it takes about 25 seconds. I think the screen capture software might be doing something. I'm not certain, but anyway, we get about 10x speed up on 16 CPUs relative to the 25. I'm using the 25 number because that's what I reliably get, but compared to 32 it would be greater than 10x. And then we look here at the original version of the function. So again, remember, it came out with recommended size of 512. We can look at the time it took, and these values are in seconds. So it took 8.8 milliseconds to allocate and push all of that information to the device. So pretty fast. Well, slow to a computer, but fast to a human. And it took 1.4 milliseconds to actually read it back. But to actually run the calculation, it took 1.2 seconds. So maybe a little under 2 times slower than on 16 CPUs, but it's on the order of 20 times faster than running on a single CPU. So already there we're getting a huge performance increase over a single CPU. So that's actually quite good. And then I also want to point out that the numbers that we're getting back for the accumulated values are identical so far. So the total runtime for the GPU loop unoptimized was 2.32 seconds. So it's actually, if you compare it to the CPU loop, all the overhead and things like that, we're getting, maybe it's not a win in this case, or again, depending on how you look, if you're queuing a bunch of these kinds of things, it may end up, the overhead diminishes, and so it may end up being a win-win. This is why you want to print out these kinds of statistics. Now, let's look at the optimized version of the kernel. If we look at the optimized version of the kernel, again, recommended size is 512, so that hasn't changed. Write and read times are, close to the same. These numbers will fluctuate a little bit, but if you look at the runtime is 0.125 seconds, so 125 milliseconds to run the exact same kernel. So it's 10 times faster than this, and it's about 200 times faster than this guy. So that's a pretty big performance when we get the exact same answer again, and it's really, this is, hopefully will show you, and the only difference between this one and this one, of course, is the fact that in this case, the optimized case, we're using our shared memory version. That's it. This is the exact same code that was in the presentation. So that's the only difference between these, and so hopefully you can see that that this, using the GPU and optimizing your code for the GPU is really worthwhile. So with that, sort of end the demo. You've got this code. You can download it, play around with it. Again, I do want to point out one thing, very, very important, that if you have a system that only has one graphics card in it, be very, very careful when you run these examples, because what will appear to happen is that your system may appear to freeze depending on how long it takes for this to run on your system. Okay, so be very, very careful. Your system probably has not frozen, but remember, graphics cards cannot be preemptively scheduled. There's no preemptive interruption on a graphics card. So if it gets a whole bunch of stuff that it has to run and do, it's going to go and do that, and it's going to wait to service any other graphics request until those commands are done. And so you may be sitting there and it'll be like you can't move your mouse, or you might be able to move the mouse but Windows aren't responding, or things like that. Your system isn't frozen, your graphics card is just busy. So ideally you would have 2 graphics cards in your system, okay? But if you only have one, what you may want to do is tune down these numbers substantially, just in case, just to be on the safe side, to get the, until you're comfortable with, that it's executing and you get some feel for how long it's going to take for these various stages to run. Or you might want to just not run the GPU portion or something like that, and just look at the code or something like that. But it's better to have 2 graphics cards. If you have like a MacBook Pro with 2 graphics cards, you might want to set one graphics card to be the one obviously that displays, and then use the second graphics card for OpenCL. And basically what you'd have to do is pull from multiple devices instead of one, whichever one OpenCL finds by default, perhaps even just switch over, use that one for OpenCL, but then make sure you're actually viewing your screen with the other graphics card. So both of the graphics cards in the newest MacBook Pros and the dual MacBook Pros, dual GPU MacBook Pros are OpenCL capable. One's faster than the other, obviously, but anyway, so that's where you would do all that. So please do not email me and say, oh no, you froze my system or something like that. It's not frozen, but the graphics card will have gotten consumed with instructions. And if it gets really kind of messed up or confused, you may have to force reboot. So you really want to avoid that. Another way to do this is if it's running and the system does seem to get bogged down, you could probably you can still SSH into the system, and then you might be able to kill the process and then regain control over the system. But again, try to avoid that as much as possible. But you've been warned, so just be careful when you run this. So anyway, that's that. We'll switch back to the presentation, finish up, and go from there. Okay, so hopefully that makes sense. You see, how the projects are set up. You see, obviously, the kernels, what's happening in the sort of various stages, and you see the benefit of using shared memory in terms of performance. So I really hope that this makes things a lot more clear for people if they were having trouble with this conceptually, and but if it doesn't, certainly ask questions, and I'll try to address them and try and come up with other examples. But I think this will really sort of drive the concept home for a lot of people. Finally, so what I'd like to end up with is, again, all of this information is available on MacResearch.org. You can download the other podcasts if you haven't. You can subscribe to this via iTunes. There's instructions on the website for how to get to this via iTunes. So you can get notifications that way. There's an RSS feed, etc. and so forth. We have an Amazon store, so we get a little bit of a small percentage back on any purchase you might make through Amazon if you buy it through our Amazon store. If there's something that you want to get that's not up there, and let me know, and we can we'll add it, and you'd really be helping us out. Everything that you buy comes back and helps us cover costs and take care of things that we we couldn't do otherwise. We're not for profit, of course, so we don't have much revenue. So anyway, anything that you can do via the Amazon store would be through our Amazon store would be great help to us. It doesn't cost any more if you buy it through our store directly through the Amazon store. The only difference is we get a little bit back. So if you do that, or if you have done it, thanks. We really appreciate it. And then finally, again, just a reminder, you can go to the Kronos Group website. They've got they have the OpenCL spec up there. They've got a little cheat sheet card, and then some other information about OpenCL. Great resource, great thing to go to. So check it out. And that's it. We'll see you next time. I'm not certain just yet what we'll talk about next time. I'm still thinking about it. But if you have questions or suggestions for a podcast, let me know, and I'll try and see what I can do. So until then, have a great week, couple weeks, good day, and I'll talk to you soon.